check means it looks like you put in a good amount of effort, and that you've gotten pretty much what I wanted you to get out of the homework. A 0 means like it looks like you wrote your name and passed it on a blank piece of paper, or maybe not much more than that. A half will be, you missed a lot of it. There's something going on. It doesn't look like you didn't put in nearly as much effort as somebody else who completed the assignment. So it's, like I say, mainly the homework. What should benefit you from the homework is my feedback. I'm going to write stuff on the homework, and I'd really like you to pay attention to what I write on there. I'm not going to be able to grade every problem in every homework. In fact, I'll probably grade less than half of the problems in the homework. But I'm going to pick out particular ones that I think are especially important, and I'll write on those. Even if I think you've got it almost perfect, I'll always find something I think you can improve on. Right? So you count. There's going to be some red stuff. Yes, sir. C notes, and that's a check. C notes, meaning the notes that I've written on there. Can't read my handwriting. Do that. Mr. Sharp.
Yeah, I did.
Yes, please turn in your homework there, and you can pick up the solution as well. Just once. Let's see. Mr. Tremblay.
If you wanted to do like a group study sometime,
I kind of get in halfway through this. You said check full credit.
Correct. A check or a +1 is full credit.
yeah, go ahead.
A half means half credit. And the way I do the homework grade is I add up the points, divide by the total possible, and that's going to be some fraction of your total grade. So most students, if they just keep doing the homework, they should get virtually 100% on the homework portion if you're, making good effort. Excuse me, sir. Let's see. We're on. Okay. Good. Let's see. Okay. We're moving through Chapter 1. We're about halfway through it. There will be an exam in class on Chapter 1. Test in class on Friday, September 6th. So a week from Friday. That allows enough time for you to pass in homework. This is for you. It allows you time to pass in homework, give me a chance to grade it, turn back to you, and still another class period for questions if you have something left over. So the chapters will overlap. That is, we'll start the next chapter before you have the test on the previous chapter. It's going to be like that all the way through. But you'll find the material is very cumulative, so it all kind of starts blending in together. There's a lot of stuff. Each test will be actually on all the material. Each term, each test will be since the beginning of the term. Okay, let's see. And Ms. Shaban, homework and solution. Right here. Just pass those in. Okay, so let's see. I sent out an email with office hours. Prior to that, I had sent out a doodle to try to find out what were convenient times. So office hours are set now, various hours on Friday. So Friday morning, a couple of slots. Friday afternoon, before and after class. I think there's a lot of time on Friday. It seemed like everybody, at least most of the people who responded, almost everybody who responded liked Friday. So that seemed to be the best choice. One more used book is available. Still the same used book is available. The student who had it wanted me to let you know that nobody's asking for it yet. So if you want a copy of the used book, if you haven't made other arrangements, let me know and I'll put you in touch with them. SPS officers are coming to class this Friday, to introduce themselves to you and to and to give you an introduction to this SPS, Society for Physics Students. And you don't have to be a physics major to join. So they're coming for a couple of minutes on Friday, right at the beginning of class, to let you know and invite you to their meetings and stuff. I highly recommend it. I think it's a great thing for you to be involved with socially and otherwise. They're pretty active, and the activity depends always on students. It's a student-led organization with some advice from a couple of faculty who are involved, and support from the department. The department does support the SPS. So that will be on Friday. Okay, some of the homework that I handed back, and there were a couple of questions that I wanted to go over before we go over to the homework for today. The first one was just so everybody's on the same page on this. What do we know without prior use of our senses? It's a very simple answer. Nothing. And some people came up with some inventive things that they thought that they could know without prior use of your senses. But I think you'll see, if you think about it for a while, everything you know, you learned about through your senses. There isn't any exception to this. It's just a human way of doing things. There isn't any way around it. So, does everybody see that perhaps now that we've discussed it a couple of times? Is there some difficulty? Is there something that everybody okay? Does it make sense? In fact, listen to that. Does it make sense? It's in our language. It's an indication that we acknowledge. That's almost the same thing as understanding, right? Does it make sense? Do you hear what I'm saying? Can you see what I mean? Right? It's built into the language. We acknowledge this use of our senses in communicating and understanding and learning. That's about the only way we can do it. I'm going to close this door. I did put in a request to fix this air conditioning, and they did something to it, and it is a little bit cooler today, but feel free to turn the fan on if you need it. And so it's about 2 degrees cooler than it was last time we were in here, but it's not cool enough yet. I'm still working on it. Okay, the next thing. What is the modern scientific method? You've heard a lot about the modern scientific method, I'm sure. Outside of this class, virtually every science class you've ever taken has something about that in Chapter 1. What have you heard before this class about the modern scientific method? What is it? Yes, sir. Mr. Jackson.
You observe, you make a theory, you do experiment, test results, and come to a conclusion.
Right. Observation, hypothesis. What else was it? Hypothesis, testing, experiment. Is that it, pretty much? Conclusion from the experiments and the comparison to the hypothesis. Yeah. This is hokum, I think. Because if you look through the history of science, all of these things were done before the modern era. Observation, hypothesis, experiment, conclusion. Measurement is not listed here, but that's really an important thing, right? Measurement, that was done before. I mean, Aristotle was wonderful at virtually all of these things. Maybe experiment, he didn't do quite the same kind of controlled experiments that came later, but there were a lot of experiments being done before Galileo, for example. This is a cartoon image of the modern scientific method, and I think it really misses the point. So in Chapter 1, Rizzi, I think, hits the nail right on the head. He doesn't call it the modern scientific method, I don't think. He gives it another name, but it is the modern scientific method. The empiriometric method really is the modern scientific method. And what is the empiriometric method? It's looking at nature specifically in a quantitative way, so it brings in measure. And the second, probably more important part, I mean, measurement is obviously critical, but that came before. The part that was missing, the added ingredient, was math. That's, with Descartes, that's really where the whole thing takes off. The use of systematized mathematics with symbols, using symbols to represent measured values, for example. So the empiriometric method, measure plus math, and of those two, measure is certainly necessary, but the new ingredient was the math. That's modern physics. If you really have to hone it down to something, it's the math, right? I mean, when you talk about string theory, people want to talk about string theory to find out you're a physics major. What do you think about string theory or something, right? It's math. In fact, the problem is maybe it doesn't have anything to do with reality. Maybe it's all math, right? But that's it. You know, you talk about modern physics, quantum mechanics. It's virtually the focus is on the mathematical. General relativity, heavily mathematical. These developments that take place are focused on the math. That's where the crucial part is. The experiments are a necessary part. The measurements are a necessary part. You can't proceed without it because the math ultimately relates back to the measurements. So it's a necessary groundwork. But the understanding is always in terms of the math, at least in the modern context. We really feel like we understand it once we have a theory, a mathematical formulation of this. And it's not until we have that we really feel like we've got an understanding of it. Now that's to put as emphasized by Rizzi. The problem is you don't want physics to be solely the mathematical part. You have to provide the context, which is what this course is very good at providing both. The mathematical part, but the context that goes around it, that really fleshes it out. Because the math is up here, and it's the connection to the physical that's necessary to understand what's going on. Okay, how about, we talked about measuring quantity, and I didn't quite complete what I should have written down for you. Sorry about that, but let's do it now. Measuring quantity. A measurement is a relation. That's in the text. What's going to be added is a measurement is a relation, an analogy to number. I believe I wrote that down. A relation, and an analogy to number. We talked about analogies. Okay, so let me give you an example of this. I take a ruler, say a meter stick, and I go 1, 2, 3. So I've got the length of the table has been measured in relation to that meter stick. So here's the analogy. The length of the table is 2, the length of the ruler. And that is the same as a numerical relation, 3 to 1. That captures the essence of a measurement, all of that together. Now we reduce it. We just say it's 3 meters. What's implied by saying the length of the table is 3 meters is that the measure of the length of the table is 3 meters. Specifically, it means that there's this relationship between the lengths that's like, in some way, analogous to, in some way, the relation between two numbers, 3 to 1. So there's a 1 here, which is the unit of measure. And then there's the thing we're wanting to measure. But we have to find two objects that share the same attribute. If I wanted to measure the length of the table, I wouldn't be using red, something that's red. You know, I've got a red color, and I'm going to compare the redness of this to the length of that. That doesn't make any sense. I have to have something that shares the attribute of length. Well, every changeable thing has quantity. So I can always measure quantity. And that's the primary understanding of measurement, is when I measure quantity. So I could measure area by taking something else that also has an area, a unit area. So I take a little tile, and I measure out the area of that table. Same thing. The area of the table to the area of the tile is 20 to 1. That would be a measure of area. Do the same thing with volume. Take a little cube. Okay. Quantity is easy to measure because it amounts. But what about quality? We can measure qualities, some qualities. But qualities don't amount. So how would we go about measuring quality? It's by analogy. It's an analogous process, but it's not the same. Sorry? Intensity, exactly. Very good. Yes, sir. That's very good. I'll let you hold it and pass it around to the next person, please. Intensity. In quality, some qualities vary in intensity. Like something is red and something is redder. Something is hard and another is harder. So is there a quality scale based on hardness? You know what it is?
A Mohs scale.
Mohs scale. Mohs scale takes a set of minerals. Everybody familiar with Mohs scale? Not really, no. Okay. It's a way of taking minerals that are found out in the field. It's something that's very easy to do in the field. You take two rocks that you find, and you want to find out something about them. So you can take, well, actually take one rock and you against the set of known minerals in your kit, and you try scratching the known ones, or taking the known ones and scratching that one, and so it will fall in some scale of hardness. Diamond being the hardest, tungsten's very hard, really soft is chalk, and some other really soft things. Sandstone somewhere in the middle. Yes, sir?
What's the difference between that and rock wool? Isn't there a rock wool hardness scale?
There are lots of hardness scales. Mohs, I think, was the first that I know of. And it's really easy to use out in the field. So a field geologist will carry a Mohs kit. At least they used to. Carry a Mohs kit, find some mineral, he wants to figure out what it is. So he does, one of the things he does, aside from the color and the texture, is the hardness. And by that he can help to evaluate what it is he's got. Is this a piece of gold or fool's gold or something like that, right? Mohs scale of hardness then allows you to order by hardness from softest to hardest, and to assign a number. You know, it's between a metal like copper and another metal like tungsten or something. So you assign numbers to the standard ones, and you find it's in between somewhere. So and you can get fine gradations of this. There are other scales of hardness. Engineers use another scale. Material scientists have another scale. So actually several of them. But this one is easy and convenient, but it gets the idea. So you can assign a number to the hardness that way, like the Mohs scale. So qualities can be done that way. Even colors, you can assign numbers to colors, right? 25500 is red, I think. Is that right? I think that's red.
So the different ratio to red, blue, green,
Yeah,
or red, blue,
right.
yellow.
On 256,
That's red, blue, green, I think.
0 to 255, yeah. Okay, so that's the way of assigning a number to an intensity of a color. 250 is less intense than 255 in redness. So. Okay, now, however, let's ask this question. So I can assign numbers to quality, but you see it's kind of analogous. It doesn't have the same physical meaning that quantity does, because colors don't amount like lengths do. But here's the question. There was a question on this. Is quality essentially reducible to quantity or a number? What do you think? Keyword, essentially. In essence, can color be reduced to a number? If I give you 25500, you may know that by some other association that somebody means red by that. But does that really capture the essence of redness? No. So qualities are not essentially reducible to quantity. Neither is number. Nor number. Qualities are not essentially reducible to numbers. Even though you can associate a number with a quality by a measurement process, you do not capture the essence of the thing. It's just not there. Okay. Yes, sir. Good.
Can all qualities be measured through association?
No, I don't think so. I don't think all qualities have intensity. There are qualities that don't have varying intensity. There must be. I think if I stop and think about it. But a lot of qualities that we talk about in this class do vary in intensity. And so, so they're measurable. But just because something is not measurable doesn't mean it's not meaningful. That's another mistake. Physicists especially get used to measuring things, so they can't measure it. They think, well, it's meaningless to talk about it. That's a common reaction among the community. You can't measure it. What is it? You can't measure it. A famous physicist, let's see, he's misquoted actually. He didn't say this, but it's often misquoted as saying, you don't know something until you measure it. He didn't actually say that. That's this was Kelvin, or Kelvin, no. Yeah, I think it was Kelvin. Is often quoted as saying that. He doesn't say that. He says something is more subtle than that. But he is going in the direction of saying that a quantitative measure is necessary for making progress in physics. But the misquote is that he's saying you don't really know something until you measure it. But that's backwards, right? You can't conceive of making a measurement until you know what it is you're going to measure. Right? We demonstrated that in class with some simple examples. Okay. Another thing, science and technology, that's discussed in the homework, the relationship between science and engineering and technology. Robotics is not science. It drives me nuts when I see somebody talking about science class. They're going to introduce kids to science and they give them some Legos and make them build a robot. No, that's not science. I mean, they're learning something about mechanics or electricity or something. Yeah, but that's not really the purpose of this thing to make a robot, is to make a robot. That's engineering. It's technology. It's not science. And that distinction is lost, I'm afraid, on most people these days, unfortunately. They equate the two. I think it's very important for us as scientists and engineers to resolve that difference between them, science and engineering. One is for the sake of learning. Why is it good for us to learn?
So we can apply.
So we can apply. That's the engineer. It's good for us to learn without applying even. Why? Because we're rational animals. It fulfills us. It perfects us as reasoning creatures to know about the world around us. And that's why it's good. Just because it's what we're made for, to know the truth. Now, there's plenty of good things you can do with this stuff that we learn. And it's wonderful to apply them. And that's another step. And in that sense, the goodness of what you do as an engineer depends on the goal, right? The goodness or not depends on what you're going to do with it. But learning is always good. No doubt about it. Learning is always good. Okay. And to illustrate that point, number 2 son, one night at dinner, he was eating his supper and he was complaining about math class. When am I ever going to use this again? Yeah, has anybody done that this year? Probably fewer of you, maybe, than if I went to another class.
Yeah, some a physicist.
What's that?
Not to a dad who's a physicist.
There you go. He made a fundamental mistake in that. So I said, well, okay, do you like that pork chop you're eating? Oh, yes, sir. Mom's a good cook. He loves Mom's cooking. Still does. Good cook. I love those pork chops she makes. Are you ever going to use that again? And he's, that's kind of a weird question. What do you mean we're going to use it again? Well, it's the same question. That pork chop, what happens to the pork chop when you eat it? It becomes a part of you, right? You grow. It increases your quantity. Hopefully not too much, the right proportion or something. It gives you the strength, ability to do something more. But you're not going to really use it again. I mean, but that's the same thing with learning, with math, with physics. When you learn it, it becomes a part of you. It expands you in a way that you can't really tell outside, but it expands you in a very radical way, in a way that's very human. Right? That's what this class is about. I want you to learn. And the emphasis is on what goes in up here. And my problem is always to try to find evidence of what's going on up there. Give me some concrete evidence. I want to see something here. Aristotle says, a good sign of learning, a good sign of understanding is teaching. So the best way I could do that in this class would be to have each one of you teach some part of this course. We just don't have time for that. But that would be how I would learn real quick, whether you know it or not, is to let you try teaching it, right? And if you can teach it, then you've gone a long way to understanding it. So there will be questions on the test where I will say, explain to another physics major not in this class what is quantity or quality or substance or something like that. So in other words, think about yourself before day one in this class and explain it to yourself. Imagining that you haven't been through all this instruction and reading that we've done in this class. That's going to be on, I guarantee, almost every test. It will be something like that. Explain substance to a student who hasn't had this class. Physics major, somebody like yourself. Okay? And what I'm looking for there is evidence of what's going on up here. I want understanding. I want concrete evidence of understanding. They call it learning outcomes when they're doing other things, but that's really, to me, is kind of nebulous. I'm looking for a good explanation. Explain this. That's a good task, I think. Okay, what did you think about today's homework?
It wasn't 41 questions.
Take you less time? Is that what you're telling me?
It wasn't too bad. I mean, some of the stuff was kind of interesting.
20 questions. What's the purpose of the 20 questions question? First question. What do you think that's about? How many? There may be people in here who have never played 20 questions. In which case, that one might have kind of escaped you. But, the point of 20 questions is for one person to think of something, and you're supposed to ask them yes or no questions to figure out what it is they're thinking. Well, we're going to narrow this down because we're going to apply it to properties. So you're going to use the categories to try to figure out what property this person is thinking of. So the example that's in here is yellow in the solution. Yellow, thinking of a property. So I'm going to think of yellow. And then you would ask me first, well, a good question might be, is it a substance or a property? That narrows it down because it's got to be one or the other, substance or a property. I guess it could be, instead of a substance, could be a group of substances or a part of a substance. Those are other possibilities. But in this case, it's determined right away as a property. And then you just can start going down the tree. Is it intrinsic or is it extrinsic? Well, in this case, color would be intrinsic. Is it quantity or quality? Okay, you have to do this yes or no. Is it quantity? Yes or no. Then you know it's a quality. It's not quantity. Okay, then qualities are things that are easily accessible to the senses. So you start finding out qualities, are they, what sense? Is it related to taste? Is it touch? Is it related to one of those? Sight in this case. So then you start narrowing it down within sight. So you can see there's subcategories of qualities. There's lots of qualities. Not all of them are easily sensed. Okay, so he narrows it down. In this question, it's narrowed down to yellow. Okay, and that relates also to the subcategories of quality, loudness, color, hardness, temperature, texture, lots of qualities. Powers, abilities, lots of qualities. Any questions about that one? Is that informative, that question? Did that help you to understand the categories a little better? I think it is. Yes, sir.
How would you categorize something like time as a substance or property?
So time, yeah, good question. So time fundamentally is a property because you speak of something in time, something being somewhere, some way at some time. Okay, so fundamentally it's a property. We also speak of it as a measure, and this is an equivocation. Okay, here, univocal means one voice. Univocal means having one meaning. There are words that are univocal, meaning they have one meaning only. Look in the dictionary, that's it, one meaning. Equivocal or equivocal, multiple meanings. Therefore, there are multiple definitions in the dictionary. An analogy is an equivocation, but a controlled equivocation. Because you say Fifi is healthy, Fifi's hair is healthy. Those are related meanings of the word healthy. So it's controlled in that sense as an equivocation, but it's controlled because there's a relationship between those different meanings. Okay, so now, how did I get off onto that? Your question was, I'm sorry, I am answering your question, but I lost the question.
Time.
Time, thank you. So time has multiple meanings in the sense that it's a category. It's simply that it's when something is. Okay? But we also use time to be a measure of change. We talk about that as a measure of change. Time is also described as a measure. So it has a slightly different meaning, and in that case, it's not a property exactly, it's a measure of a property. That's an important point. A property is not the measure of a property. Let's see, the measure of the property is not the property. Oh, dang. Ooh. All that stuff. There we go. Okay. All right, well, here's the best way I can illustrate that for you. Forgive my sons are a lot better artists than I am. What is that? Think again. Oh, drawing of a cat. Okay, it's not a real good drawing of a cat, but it's a drawing of a cat. Not a cat. It's not a cat. It's a drawing of a cat, right? I could show you a better drawing of a cat. Still would be a drawing. It's never going to be a cat. It's going to be a drawing of a cat. Now that's a metaphor of trying to get you to understand the measure of the property is not the property. The measure of the length is not length, it's a number. Right? And length is not fundamentally a number. It's a quantity, not fundamentally a number. So when we speak of measure of time, that's not fundamentally time, but it is related to time. We're going to find this over and over and over again. We're going to encounter properties that we discuss, and we're going to talk about how to measure those properties. And we need to remember the measure of the property is not the property. We need to remember those are different things. Okay? And so time has both meanings, though, as the property and as the measure of the property. And that's a funny thing, that we have this one word that means two different things that aren't quite the same. They're related to each other, but not quite the same. So it's kind of analogous in a way. Okay, because a measurement is an analogy. Good question. Okay. Let's turn to the distinction between a substance, part of a substance, a group of substances, and a simple property. So you have a list here. This is number 5. A frog. Let me ask, I'm going to put some people on the spot. Mugshots. Here they are. Okay. Let's see. Who hasn't been answering? Let's go from Mr. Tremblay.
Frog is a substance.
Good. Why?
Because it's one thing, it's one body.
Right. It has everything it needs to be a frog. Right. Not really lacking anything, doesn't need anything else. It doesn't really have more than it needs to be a frog. It exists of itself. How about Mr. Vestal? What about an iron screw?
Substance.
Good. Why?
Because it exists without any change.
Yeah. Now, what about the fact that it's got, it's been machined and shaped and molded and stuff?
Still screw.
Still a substance, isn't it? It's been given an artificial shape. So it has, the shape of it has been altered, but not so that it changes essentially what it is. It's still just a piece of metal. It can be useful, it can be used, it's still metal, a hunk of metal. You like ask, what is the nature of that thing? Piece of metal. And in fact, we use metal for screws because they have the right nature. They're kind of tough, don't yield easily, they're not bendable. You can make screws out of plastic, but they're not going to take much stress. A nice piece of metal is going to take more stress before it breaks. Right? So that has to do with the nature of the material inside, not the shape. Yes, sir.
What about if it rusts? Does that become then a group of substances?
Yeah, that's a good question. So I think at the beginning we're going to find lots of these questions. Oh, what about this and what about this? So I think when you're first being introduced to this, I think we stick with simple cases where it's pretty clear what's going on. And not that we don't want to investigate these other cases, but I think I want you to get comfortable with the clear cases first. Now, generally, to answer a question like that, you have to know more specifically about what's going on. So you may have to apply, may have to investigate more, get more information about the nature of the thing. Okay, so that's the general answer to that. But I want to hold off giving a specific answer. Okay, well, we can come back to it later. Computer. How about Ms. Watson?
It's a group of substances.
Good. Why?
Parted it out. It's still, that part of it is still
Yeah.
itself.
Even a Mac is not a substance. Even a Ferrari is not a substance. I know. It seems disappointing. It's not a substance. It's a group of substances. It has no unity. The structure that it has comes from outside. Whereas for a thing which is a substance, the structure that it has comes from within. A frog becomes a frog from within. Uses nutrients, grows stuff absorbs stuff from without, but the organization comes from within. Whereas a computer, the organization is imposed artificially by a person. So in that sense, I have a computer science friend, and I drive him nuts when I tell him computer science is just barely a science. It drives him nuts. I say, because science is about nature, natural things. And a computer doesn't exist naturally. It only exists up here. It drives him nuts. Doesn't want me to say computer science is not science. All right. So, I haven't convinced him yet. He wants computer science to be a science because he knows it. Yes, ma'am?
What would you consider it if it's not a science?
Okay. So, it's certainly a study. So, by science, I'm meaning the sense of knowledge of natural things. Now, you could broaden that to mean the knowledge of just knowledge, generally speaking, even of artificial things. Okay, so there could be, I guess you could say, automotive science and science of artificial things. In which case, art would be a science, right? Painting would be a science, right? But we don't say that. We say painting is an art, right? Again, there is an equivocation involved in that, but I think the primary meaning of science should be what is natural. And we tend to take that meaning and apply it to things that are just rigorous studies of. Right? That becomes a science. But I don't think that's the primary meaning of science, because primarily what we know are natural things around us. That's primarily what we know. And primarily what exists naturally are those things. Computers, as I say, computers and artificial things exist as parts of natural parts put together in a certain way, but the conception of what it does as a computer is entirely up here. Same thing with a dollar bill. Like, take out a dollar bill and look at it. Naturally, it's a piece of paper with ink on it. The dollar bill has no nature as a dollar bill, right? It's a piece of paper. Okay, I know there's some puzzled looks. I know this is probably the first time you've heard anybody say something like this. If you think about it carefully for a while, you'll come to agree. Okay, your toes and hands. Ms. Swanson, how about?
Parts of the substance.
Yes, why?
In the answer, I think I said, if you remove it, then it won't be really that thing anymore.
That's right.
It's different.
It is what used to be your toe. Right? A corpse is a mortal remains of a person. It's not a person. It is what remains of the person after death. What's left here. So, how about carbon atoms? Mr. Sharp?
Parts of a substance?
Yes, sir. Why?
Because I really don't know.
It's really not any different than what she said, is it?
I guess not. No.
So the carbon is bonded in a way that alters it substantially. When it's connected inside there, the atoms inside your body are altered in a way significantly. And that bonding is important. Your body uses that. But they're just parts, like all the other parts. They're very small parts, but they're parts that have been bonded together and they're organized. The word organ describes that. My parts are organized. And so we talk about organs. That's what the meaning is. Organs are organized to the life of the whole. All of my parts, all of your parts are organized to your oneness, to make you one. And to the extent that they are parts of the whole, they are subsumed into the whole. That's true for the atoms as well. Their being is subsumed into the oneness. Otherwise, you wouldn't be one. You'd be all these parts. If there is a oneness there, and there is, then you have to understand that the parts have a relation to the whole that's like what we just described. How about big? Miss Shaven.
A simple property.
Yes, ma'am. That one's easy. Miss Ma, clock.
It's a group of substances.
Like a computer or a telephone or anything else. And Mr. Krieger, yourself?
A substance.
You have unity. It is one. How about this class? People in this class. Group of substances. Okay. Let's go down to what can you think of that is not describable in terms of the categories or analogies to them?
Adverbs.
What was that again?
Adverbs.
Adverbs. For example?
Quickly.
Okay, I guess that's true. I gotta think about that. Quickness certainly would be a property, but quickly, I guess. Okay, I'll provisionally accept that one. Any others? Yes, ma'am.
I said like an idea.
An idea, yeah. An abstraction, a concept. Yeah. Okay, now, as an example of that, a logical proposition, a syllogism. Maybe you've had logic, a syllogism. If, let's see, Socrates is a man, all men are mortal, therefore Socrates is mortal. That's the classic syllogism. It exists only up here. That does not exist as an object, an objective thing. Can't be categorized. So concepts, and certainly extensions of concepts into logical propositions like that. Transcendentals such as truth, beauty, and justice are things that are not possible to put into categories like these categories of existence that we're talking about here, properties. They don't have size. An idea doesn't have quantity, does it? So an example of an idea would be animal. Now, animals have size, but the concept itself doesn't take up any space. So it has no quantity even. And quantity is the fundamental property of physical things. So an idea is not a physical thing. The concept is not. Okay. How about the boat? You're going to measure a boat using fish. What aspect of the boat might you measure using a fish? Try Mr. Hodgkiss. What aspect of a boat might you measure using a fish? Length. You can measure the boat in fish lengths. Why would that be nice to know?
I guess it's easier to, think of, people know how big that fish is, and instead of saying, it's 30 feet long, people aren't going to automatically think, okay, it's this long. You have to, see something that's 30 feet long so you can compare it.
You might want to know how big a boat you need. Right? Jaws. We're going to need a bigger boat. Right? What else could you measure about a boat in fish? Weight. Pardon?
Weight.
Yeah. Now, Now you could actually measure the weight of the boat in fish weights, but there might be something more important than the boat weight itself. Yes, Mr. Rose?
Volume.
It's volume. Why would that be important?
Because you want to know how much you could get into the boat.
How many fish can you get in the boat? Yeah.
If you fishing, you want to know how much fish I'm going to put in so I can eat tonight.
That's right. Exactly. Right. There's another thing about a boat. Let me see if I can pull out another one. Another thing about a boat that you might want to know that's related to weight.
Buoyancy.
Yeah, buoyancy. Good. Why would that be important to know?
So you continue to flip, it'll sink.
Yeah, that's right. How many fish can I get in the boat without swamping the boat, right? That's not the same thing as the volume of the boat, right? That's the buoyancy of the boat compared to the weight of the fish. How many fish can I get in this boat? So heavy fish, dense fish, you get fewer of them. You know, puffy fish, you can get a lot of puffer fishes in the boat. No problem. Okay. How about hardness? Could you measure the hardness of the boat with a fish? Mohs scale, scratch the boat. Make the boat scratch the fish. Silly, but you could, right? I guess you don't want to scratch the boat with all these fish, so you want a durable boat. You have hard fish, soft fish would be more problem. Okay, but you see, there are lots of aspects, and the key ingredient here is that the two things share in the attribute. That's the only way you're going to get a measurement out of it. They have to both share that, and the key part of your brain, your mind, is saying they have that attribute in common, so I can relate them that way. I can use one to measure the other one. And quantity is always that way with physical things because that's the base property. So quantity is fundamentally what we talk about when we measure, but there are lots of things that are qualities that get misnamed as quantities, and we'll talk about those. Good, okay. A couple of things having to do with units, converting units. Cubic feet to cubic yards, that sort of stuff. Yes, sir.
In summary, I believe it said that temperature was a
Quality.
I believe it said it was a quantity, and that's what my question was.
Should be quality. See if you can find that for me, please. You have, yeah. See if you can, Mr. Jackson's in the summary. Okay, any questions about converting units like cubic feet to cubic yards? Come see me if you have a question about that. I'm assuming most of you have done that sort of thing. You know how to do it. If I'm wrong, come see me. Take that to the Physics Learning Center. That's a good thing for them to help you with.
Right here, underlined, it says, for example, in this way, distance, pressure, speed, temperature, intensity of light can all be called quantity.
But, okay. In this way, what did he mean? What was preceding that? I'm glad you read the summary. That's good.
He was talking about measurement and treating quantity and
So let's read that paragraph. By measurement, we can think of all aspects of physical things as numbers, right? Even though they aren't numbers, but we can think of them and more deeply incorporate, though by analogy, mathematics into our understanding of the physical world. In this way, all variety of properties and combinations of properties and even motion can be treated as quantity in an analogical way. For example, in this way, distance and temperature and so forth can all be called quantities, even though they're fundamentally qualities. Okay. Yeah, and it's good to have that good in your mind. Okay. And we'll come to in chapter 3, the first quality that we'll be talking. One thing will really be clearly quality. Actually, several that are often mistaken for quantity. Okay, the last problem I want to spend a little bit of time on. If I tell you how many molecules of air are in this room, you can estimate it. Like if you know the number and you know the size of the room, you can estimate the distance between the molecules, an average distance. So how would you go about doing that? If I give you the volume and I tell you how many, how would you get the average distance between them?
I take the volume divided by the number of molecules.
Good. All right. Now is that a length? Is that a distance? It's still a volume. It's a volume per molecule. Yes, ma'am.
The total volume of the room minus the total volume of the molecules then divide that.
Why is the volume of the molecules even important? If you want to know the distance between molecules, they could be big, they could be small, but you're just concerned about the distance.
If they take up space.
You're worried about the space between them, the distance between their boundaries. I mean from center to center.
Oh, never
We
mind.
don't need to know. Okay, so let's make it simpler. Just center to center distance between the molecules. What's the average center to center distance? Don't need to know the size of the molecule to do that. So I've got the volume per molecule. Now what do I do with that? So imagine that I laid them out in a very ordered pattern. I put them on a cubic array. That is, I put them on a lattice, and I have a bunch of cubes, and I put one in the middle of each cube. So I divide up the room into little cubes, and I put one air molecule in each cube. So what's the size of that cube? The volume divided by the number, right? This is the size of the cube that each molecule would take up. Now, how do I find the distance between them?
Divide by square root. Take the square root.
It's a root, but not square.
Fourth root.
Cube root.
Cube root. Oh,
Take the
God.
average of 2 and 4. It's the cube root, right? Take the cube root. Is that a length? Right? Volume is cubic something. Cubic centimeters, cubic whatever is a volume. Take the cube root, it's a centimeter. Right? That is a length. That's a good guess, order of magnitude guess of the distance between the molecules. So he's getting at, this is an exercise in dimensional analysis. And your next homework Friday will be on dimensional analysis. You have a thing to download and read about dimensional analysis. We're going to do a little bit more dimensional analysis than he did in the book. So I've got 1 minute, so I'll give you a brief introduction here. So suppose I measure the length of the cube. In that example, I measure the side of that cube, the length edge of it. That will be in some distance, centimeters, meters, angstroms, something. All distances would be something like that, an inch or a foot. And I'm going to say that I'm going to use the square bracket notation. This comes from Maxwell. So this notation means the dimensionality, and again, dimensionality here doesn't mean 3 dimensions or 2 dimensions or 1 dimension. Dimensionality means type. So dimensionality, that's what they mean in dimensional analysis. Dimensionality is the same thing like type. And so that's designated as a length. Capital L means all lengths are called capital L. So if I'm measuring the length of this, it doesn't matter what units I measure it in, it's going to be a length. Okay? In the same way, an area will have dimensionality of length squared. Right? It's a product of 2 lengths to get an area. A volume, the dimensionality of a volume will be length cubed. What is the dimensionality of? So the dimensionality tells you how is it going to change if I change units. If I go from centimeters to meters, a length is going to be changed by a factor of 100. An area will change by a factor of 1,000, 10,000. A volume would change by a factor of 1,000,000. If I change from centimeters to